Hello dear students, I am Ronak Kumar, your physics faculty at Aakash, and a very warm welcome into this session in which I will be discussing the paper AIATS, that is from the series AIATS Plus 2025 Phase 2, and it was mock test 7 that was conducted on 2nd of March 2025. And a very warm welcome into this class, and I will be taking up these topics: ray optics and optical instrument, magnetism and matter, waves, oscillation, wave optics and semiconductor. So these are the topics that I will be taking up for this session, and all the topics are very important as far as your NEET examination is considered, and these topics are considered very tough from the point of view of students who are preparing for the NEET examination. So be very careful while listening to the concepts, right? Now let's move forward and let's have a look at the first problem, and it was problem 5 from the original paper. So problem 5 from the original paper, and it says that, let me give you the name of the chapter from which it is from, and it is from Magnetism and Matter, right? Now let me go through the problem for you. It says that the relative permeability of a diamagnetic material, diamagnetic substance is represented by mu r. So you have a diamagnetic substance whose relative permeability is represented by mu r, and its susceptibility is denoted by zeta. Okay. Then, so based upon this information, you need to pick the correct option. Okay. Now, dear students, first of all, you should be very thorough with. So mu r over here is your relative permeability. This term is relative permeability. Right, and zeta, this is your susceptibility. Now to comment on the relative permeability and susceptibility, you need to understand the relation between mu r and zeta. So mu r, it is defined as equal to 1 plus zeta. Right, mu r, the relation between relative permeability and susceptibility is mu r, that is equal to 1 plus zeta. What is mu r? See, we have three kind of materials with us: diamagnetic, paramagnetic and ferromagnetic. So over here I am giving you a chart which is very important from the point of view of NEET examinations. You get a lot of problems, lot of questions from this part. So here this zeta is your magnetic susceptibility. Let's have a look at the diamagnetic first. So for diamagnetic, the susceptibility zeta, it is between 0 and -1, right? Now, I told you that the relation between relative permeability and susceptibility is mu r, that is equal to 1 plus zeta. Now, for the diamagnetic material, if zeta is between -1 and 0, so you mu r, so add 1 both the sides, so it will be between 1 and 0, right? Got it? Mu r is equal to 1 plus zeta. Zeta was between 0 and -1, so mu r comes between 0 and 1, right? Now, dear students, mu r, it is also defined as equal to mu by mu naught. Mu r is defined as mu by mu naught. Now if mu r is less than 1, that means that mu by mu naught, it is also less than 1. And if mu by mu naught is less than 1, that means that mu would be less than mu naught. Right? That means permeability of medium will be less than the permeability of free space or vacuum, right? So that is for the diamagnetic material. Let's talk about the paramagnetic material. So for paramagnetic material, the susceptibility is between 0 and a small positive constant, that is E. So it is greater than 0 but less than 1. So susceptibility is greater than 0 but less than 1. So the relative permeability, it add 1 on both the sides. So add 1 over here, plus 1 and plus 1 on this side. So it becomes 1 plus E and 1. So that means that relative permeability for paramagnetic materials, it is between 1 and 1 plus E. So obviously it is greater than 1. And this mu r, again, it is a ratio of mu by mu naught. So if mu r is greater than 1, it means that mu would be greater than mu naught, right? Now let's talk about the ferromagnetic. So for ferromagnetic, the susceptibility is much greater than 1. Susceptibility is much greater than 1. So relative permeability, it will also be much greater than 1. And let's talk about the permeability of medium and free space. So obviously permeability of medium will be greater than the permeability of free space, right? So I hope you are clear with all the terms, right? So over here, if I write mu r, it is also defined as mu by mu naught, right? So this relation and this relation, mu r is equal to 1 plus zeta. These are the relations that we used to get to the answer. Now let's move to the options. So for the relative permeability and zeta, so have a look at the table. So zeta is between 0 and -1. So correct answer will be zeta is less than 0, right? Zeta is less than 0 and mu r is greater than 0. Option 3 is the correct answer to this problem, right? Option 3 is the correct answer to the problem. Someone was commenting option 1 is the correct answer. No, option 1 is not a correct answer. Option 3 is the correct answer to this problem. And yes, we have got the correct answer as option 3. Now let's move forward to the next problem. And it is a problem from the chapter of waves. And it is problem 19 from the original paper. It says that the fundamental frequency produced by a closed organ pipe. So this time they are talking about the closed organ pipe. The fundamental frequency produced by a closed organ pipe is 50 Hertz. So you have been given the fundamental frequency for closed organ pipe, which is 50 Hertz. Then fifth overtone frequency is what they are asking. Fifth overtone frequency. Okay. Let's talk about the closed organ pipe. And simultaneously, let's talk about the open organ pipe also. So closed organ pipe, right? So if the fundamental frequency is F0, then we know that for closed organ pipe, only the key concept over here is that only odd harmonic will exist, right? So if F0 is the fundamental frequency, so the next overtone will be 3F0, because only the odd harmonics are going to exist. So F0, 3F0, then next one will be 5F0, again next one will be 7F0, again next one will be 9F0, and next one will be 11F0, right? So that's how the series go. If the fundamental frequency is F0, next overtone is 3F0, next overtone is 5F0. So this is your first overtone or third harmonic. This is your second overtone or fifth harmonic. This is your third overtone or seventh harmonic, right? So dear students, you need to pick the fifth overtone. So this one is your first overtone. This one is your second overtone. This one is your third overtone. This one is your fourth overtone. And this one is your fifth overtone. So fifth overtone is 11 times the fundamental frequency. The fundamental frequency is given to me as 50. So 11 into 50 should give me 550 Hertz as my correct answer, right? 550 as my correct answer, which means that correct answer should be option 4, 550 Hertz, right? Now suppose that if I would have been given the fundamental frequency for open organ pipe. Let's talk about the open organ pipe. Right? So if the fundamental frequency for open organ pipe is F0, then what is the difference between the harmonics of closed organ pipe and open organ pipe? Here, for open organ pipe, all the harmonics will exist. All the harmonics will exist. And from this section, you will definitely get one question in your actual examination, because it is very important from the chapter of waves. So for the open organ pipe, all the harmonics are going to exist, right? So if the fundamental frequency is F0, then the next overtone will be 2F0. Again, the next one will be 3F0. Next one will be 4F0. Next one will be 5F0, and so on, right? So if this is fundamental frequency, then this is your first overtone or second harmonic. This is your second overtone or third harmonic. This is your third overtone or fourth harmonic. So if you wanted to calculate the fifth overtone frequency, so this is your first overtone, second overtone, third overtone, fourth overtone, and for the fifth overtone, it will be 6F0, right? So it will be, had the problem been about the open organ pipe, so for the fifth overtone it will be 6 into, I guess 6 into 50, so it will be equal to 300 hertz. Right? So that's the basic difference between the open organ pipe and the closed organ pipe. For the closed organ pipe, only the odd harmonics will exist, and for the open organ pipe, all the harmonics will exist, right? And I hope you know the basic formulas for the F naught. It is equal to see, if I write in the terms of length for the open closed organ pipe, for the closed organ pipe, L, it is equal to n lambda by 4, and for the open organ pipe, this one is for closed, and for the open, if I write for the open, this length L, it will be equal to n lambda by 2, where lambda is the wavelength, right? Yes, for open pipe it will be 300 hertz. L is equal to n lambda by 4. F, it is equal to nV by 4L, or it can be written as n over 4L, okay, nV by 4L. Here it will be equal to, F will be equal to nV by 2L. Right? So these are the concepts that you need to keep in mind while dealing with the harmonics of open organ pipe or the closed organ pipe. You could also be asked about the harmonics for the standing waves developed in a string, right? So you should be very clear while dealing with the chapter of standing waves, either for the case of string or for the closed organ pipe or for the open organ pipe. Very important topic from the point of view of NEET examinations. Now let's move forward to the next topic. And there you go. This is the problem from the chapter of wave optics, and it is based upon the concept of diffraction. Let me go through the problem for you. It says that a narrow slit of width 2 mm is illuminated by monochromatic light of wavelength 500 nanometer. The distance between the first minima on either side on a screen at a distance of 1 meter is. So this time you need to calculate the distance between the first minima on the either side of the screen. So this is the problem based from the chapter of diffraction. You find it a bit difficult as compared to the other chapters. So let me go through the basic setup of diffraction. So this is the basic setup of diffraction. You have a narrow slit, and light is going like this. And this graph, it shows the intensity variation. So this region where intensity is very maximum, it is the central maxima. And over here, this part is your first minima. It is on the either side of the screen. One is over here and one is over here. These are the two first minimas that are formed. Okay, someone is telling me the answer. Option 2 equal to 0.5 mm. Okay, let me calculate this, then we'll verify the answer. So this is the basic setup for the diffraction. You have a narrow slit. The light is coming out from the slit. It is undergoing diffraction. And you can see that here it is central maxima, and these 2 points are the points for the first minima. Now, if A is the slit width, then let me write the conditions for the first or for the minima in the diffraction. The condition is A sine theta, it should be equal to n lambda, where lambda is the wavelength and this theta is similar to this theta. So A sine theta should be equal to n lambda is the basic condition for the minima in diffraction, right? Now I need to calculate the distance of the first minima formed on the either side of the screen. So we are talking about the first minima that is formed on the either side of the screen, right? So for the first minima, I will write n to be equal to 1. I'll write n to be equal to 1. So if n is equal to 1, so I can write that A sine theta, it is equal to lambda. A sine theta is equal to lambda. This is the condition. A sine theta is coming out to be equal to lambda. This is the condition for the first minima for the case of diffraction. So A sine theta is equal to lambda. Now this theta is small. we have an approximation that theta is very small, right? Okay, color not visible on white portion. Okay, let me change the color. I'm telling that this theta, it is small. This theta is small. This is your first minima on either side of the screen. I have written a sine theta to be equal to lambda. This is the condition for the first minima, right? Now, a sine theta is equal to lambda is the condition for the first minima, and this theta angle is small. So for small angle approximation, sine theta is roughly equal to tan theta, right? And let me take this distance as y, and this distance as d, right? So based upon this, I can write that tan theta can be written as equal to y by d, right? And this y by d, it should be equal to lambda by a, right? Because of this. So y, that is the distance of first minima, it should be equal to d lambda by a. Y, it is equal to d lambda by a is the distance of first minima. Now let's calculate it. Y, it is coming out to be equal to d lambda by a. D is the distance between the narrow slit and the screen. Lambda is your wavelength and a is the width of the slit. Now d is the distance, so distance of screen is at 1 meter. So 1 wavelength uses 500 nanometer. All the units need to be taken care. So 500 into 10 raised to the power minus 9. And small a, the slit width, it is 2 mm. So 2 into 10 raised to the power minus 3. So let me calculate it. Y is coming out to be equal to 2.5 into 10 raised to the power minus 7 into 10 raised to the power 3. So it is coming out to be equal to 2.5 into 10 raised to the power minus 4, or 0.25 mm. 0.25 mm, it is the value of y. But you need to calculate the distance between the first minima on the either side of the screen. So here is your 1 minima, and this distance is coming out to be equal to y. So either side it will be equal to y plus y. So distance between the minima on the either side of the screen, it is equal to, it will be equal to 2y, which will be equal to 2 into 0.25, which is equal to 0.5 mm. Right, which means that correct answer should be option 2. Right. So I hope this problem was clear to you. And it was a little bit of good problem. Diffraction is always considered a very difficult topic from the point of view of students. So you need to be very clear with the concepts that are, related with the diffraction. Have a look at the diagram, try to visualize the concept, and you are good to go. Now let's move forward to the next problem. There you go. It is a problem from 26th problem from the original paper, and it is based on the concept of simple harmonic motion, right? Let me go through the problem. It says that a particle executes simple harmonic motion of amplitude a, right? If t1 and t2 are the time taken by the particle to travel from 0 to a by 2 and from a by 2 to a, then t2 by t1 will be equal to, okay. So you have been given a particle that is executing SHM with an amplitude a. You have been given 2 times, t1 and t2. T1 is the time taken for the particle to travel from mean position to a by 2, and t2 is the time taken from a by 2 to the extreme. So let me give you the diagram. So you have a particle which is executing SHM. This is my mean position. This is my positive extreme. And this is my negative extreme. Right? So it is something like this. Now, this point over here, it will be a by 2, right? And the particle starts from here, in this direction, the particle starts. So you have been given the time from 0, this is x equal to 0, this is x equal to a by 2, and obviously this is x equal to plus a. So you have been given that time taken from x equal to 0 to x equal to a by 2 is t1, right? So let us first calculate the time t1. So if a particle is starting from the mean position, what is the equation of simple harmonic motion? It's a simple thing. X will be equal to a sine omega t. Omega is your angular frequency, a is the amplitude. This is the equation of the particle which is starting from the mean position. Now I need to calculate the time taken to get to a by 2. So I'll put the value of x to be equal to a by 2. So a by 2, it is equal to a sine omega t. I'll cancel this a and a. And what is the value of that angle at which sine is 1 by 2? It's 30 degree, which means that from here I can write that omega t, it should be equal to 30 degree, but it should be in radians. But it should only be in radians, which means that it should be equal to pi by 3. Sorry, pi by 6, not pi by 3, pi by 6. Pi by 6. So omega t, it is equal to 30 degree, but 30 degree needs to be kept in radians. So omega t is coming out to be equal to pi by 6. Now if I assume that the time period for this simple harmonic motion is capital T, I am assuming that the time period for this simple harmonic motion is capital T. So dear students, I can write that omega, it is the angular frequency, which can be written as 2 pi over t, and this small t is the time taken to go for from 0 to a by 2, and it should be equal to pi by 6. So let me cancel this. So pi and pi cancel, and from here you can see that this small t is coming out to be equal to t by 12, which means that from x equal to 0 to a by 2, the time taken is t by 12. So you have got your time t1. This time t1, it is equal to t by 12. Now let's calculate the time taken from a by 2 to a. So how do we calculate this? It's simple. Let me calculate the time taken to get to the extreme. So we can also do this orally, right? See, just a second. From x equal to 0 to x equal to plus a, if the t is the total time period of the SHM, from x equal to 0 to x equal to plus a, the time taken will be equal to t by 4, right? So you need to calculate the time taken from a by 2 to a, which will be equal to t by 4 minus t by 12. So see, x equal to a sine omega t. If the particle starts from mean position and it reaches the extreme, for the extreme put x equal to a. So a is coming out to be equal to a sine omega t. Cancel this a and a. So you have 1 to be equal to sine omega t, which means that 2 pi by capital T into small t, it should be equal to pi by 2. Cancel this pi and pi. So from here, time taken to reach the extreme, it will be equal to t by 4. Right. So dear students, let me draw the diagram again. So this is your mean, this is your a by 2, and this is your a. So time taken from mean, if the particle starts from mean and goes to a by 2, so for time this time taken is t by 12, and this whole time is t by 4. So this time will be equal to t by 4 minus t by 12. And what should be the value of t by 4 minus t by 12? Anyone can put the answer in the comment box. It will be equal to t by 6. Right? Yes. So t1 over here is t by 12, and t2 over here is t by 6. And what ratio do we need? We need the ratio of, so we need the ratio t2 by t1. So it is equal to t by 6 over t by 12, right? So it is equal to 2, which means correct answer should be option 2. Not 1 by 2, we are calculating the time taken from T2 to T1. So T2 is the time taken from A by 2 to A. So you have given the opposite answer, it should be 2, right? So option 3 is the correct answer, and this is the kind of mistake that you do in the actual examinations. You have been asked the ratio T2 by T1, and you are giving the answer for T1 by T2. That will cost you a negative mark. So be very careful while dealing with the ratio. You have been given both the options, 2 and 1 by 2. So be very clear, right? So correct answer is 2. Now dear students, if I give you a chart about the time, say it's a simple chart. So if the particle starts from mean position and it goes like this, so this time will be t by 12, and it goes from this a by 2 to a, so this time will be equal to t by 6. Now it starts from extreme, reaches the mid, again this time will be equal to t by 6, and from t by 6 again reaches the mean, this time will be equal to t by 12. And this this time is t by 4, and again this time is also t by 4. So for this total time it will be t by 4 plus t by 4, that is t by 2, right? So you just be very clear with the concepts how to deal with the time, and that's how you deal with the time, right? Now let's move forward. Let's move forward to our next problem, and this is problem 45 from the original paper. It is a problem based on the chapter of Magnetism and Matter. It says that a thin bar magnet of length L has magnetic moment M, right? Now it is bent into semicircular arc, then its new magnetic moment is. So it is bent into a semicircular arc, and you need to find the new magnetic moment. So what is magnetic moment? So magnetic moment, it can be defined as small m into L. What is small m and what is L? See, small m, it is the pole strength. And what is L? L is the distance between the poles. And what is capital M? It is magnetic moment. Right? So this small m, it denotes the pole strength. This L, it denotes the distance between the poles. And this capital M, it is the magnetic moment. Right? Now, see, the concept over here is that if you are, if you are trying to mold a bar into some different shapes, suppose that in our problem, we had a thin bar magnet which is molded into a semicircular arc. So in that case, you are not changing the area of the cross section. If you are not changing the area of the cross section, in that case, the pole strength is not going to get affected. The key concept over here is that if you are not changing the area of the cross section, the pole strength is not going to get affected. So when I had a bar magnet, this is my bar magnet, suppose this is my north pole, this is my south pole, and effective distance between them is capital L. We are not taking the consideration of geometric length, but suppose that this is the effective distance between the two poles. Now this bar, it is molded into a semicircular arc. So whatever arc I'll have, the pole strength will remain same. This bar magnet, it is bent into a semicircular arc. So semicircular arc will look something like this. So this will be your north pole, and this will be your south pole. And if this is the center, and this is the center, if this is R, R is the radius of the semicircular arc, so this will also be the radius. So pole strength will remain same. That is the key concept over here. Pole strength remains same. That means that magnetic moment for this M prime, it will be equal to M. Pole strength remains the same as of this, and this new length between the poles, let me write it as L effective. So it is equal to M into 2R. The new magnetic moment, it is equal to M into 2R. Now you need to figure out what is the value of R. So if you are bending this bar magnet into a semicircular arc, then in that case circumference and the length of the bar magnet should be equal. So I can write that. Let me rub this. So I can write that. What is the length of this? It is L. And what is the circumference of this? If the radius is R, what should be the circumference of this semicircular arc? It should be equal to pi R. So L should be equal to pi R. Or from here I can write that R should be equal to L over pi. Right? So M prime was written as equal to M into 2 into R. Now in place of R, write L by pi. So it becomes 2mL by pi. Right? And the bar magnet had a magnetic moment capital M. So it means that this capital M, it will be equal to M into L. Right? So this m into L, it can be written as 2 times of capital M over pi. That's the magnetic moment. Yeah, that's the magnetic moment. That is option 4 is the correct answer to this problem, not M, not 2M, not option 3. Yes, 2M by pi is the correct answer to this problem, right? So the key concept over here is that if you are not, changing the area of the cross section, in that case, the pole strength is going to remain same. And had the cross section been modified, in that case, you have to take into consideration that pole strength would be affected. So in these type of questions, you just need to keep in mind, since the area of cross section is same, pole strength will be same. You just need to calculate the effective distance between the poles to get the new magnetic moment, right? Now, if you understood this problem, have a look at this problem. And this is the problem from the actual NEET examinations, right? And it says that, let me go through the problem for you. It says that a thin bar magnet of length L has magnetic moment capital M. So you have a thin bar magnet. Let me draw the bar magnet for you first. So you have a bar magnet and whose magnetic moment M, it is equal to M into L. M is the pole strength, L is the length, distance between the poles. Now it is bent into an arc as shown. So this is how this is bent, and its new magnetic moment will be. So you need to find out the new magnetic moment. Now if you understood the previous problem, have attempt this problem, and if you are getting the answer, put the answer in the comment box. I'll wait for your answer. So this time you have something like this. If I try to draw the arc, this is 60 degrees, and you have something like this. Okay, yeah, like this. Okay, this is 60 degrees, and this distance will be L effective. So I need to figure out the magnetic moment for this part. This is 60 degrees. So I'll write M prime, the pole strength is not going to get affected. The similar concept that I used in the previous problem. The pole strength is not going to get affected. In that case, M prime will be equal to M into L effective. M prime is coming out to be equal to M into L effective. Now the problem reduces to the fact that how to find this L effective. Now, let me find the L effective for you. So if this is R, and if this is 90, then this angle will be equal to, what? This will be equal to 30 degrees. So in this triangle, if I write sine 30, let me take this as alpha. Only this part I'm taking as alpha. So I can write sine 30 degree to be equal to alpha by R. So it is 1 by 2. It is equal to alpha by R. So alpha is coming out to be equal to R by 2. Right? Okay, someone is giving the answer. Alpha is coming out to be equal to R by 2. So the effective distance, this effective distance is 2 alpha. 2 alpha, or it is equal to R. So the pole strength, the new magnetic moment M prime, it is equal to M into R. Now how to find this R? How to find this R? Again, use the concept that if a bar magnet it is molded into this arc, then the length should be equal. Now for finding out the length of this part, I'll use the relation angle to be equal to arc upon radius. So if I find out the length of the arc, it should be equal to L. So from here I can write that arc should be equal to radius into the angle. Right? So from here, arc is coming out to be equal to radius is R, and the angle, just put the angle in radians. Don't put the angles in degrees. You are dealing with the numbers, so put the angle in radians. So it is 60 degree, it will be equal to pi by 3. So it is coming out to be equal to pi R by 3, and it should be equal to L. That was the length of the bar magnet. So from here I can write that R is equal to 3L over pi. Just put this value over here. So new magnetic moment M prime, it will be equal to small m into R. The value of R is 3L over pi. So it becomes 3 times small m into L into pi. So M prime is coming out to be equal to 3ml over pi. Now this ml it was the original magnetic moment of the bar magnet. So this will be equal to m. So m prime, it will be equal to 3m over pi. M prime is coming out to be equal to 3m over pi. Yes, 3m over pi, not 3, yeah, third option. Let me go through the options. And yes, have a look at the options. Not m, not 3m. Yes, option 3 is the correct answer, 3m over pi, and not option 4. Yes, Lakshman Patil, you are giving the right answer. Study with Brinda. Yes, option C is the correct answer. That means option 3 is the correct answer. So that's how you deal with such kind of numericals. In the original numerical, you had been given the semicircular arc, which was a bit easier to deal with. Semicircular arc ki length nikalna was not a very difficult problem, but this time they have given you an arc which was subtending an angle of 60 degrees at the center. So a little bit of concepts were involved in this. The key concept was that pole strength was not going to change. So you calculated the L effective and how to get to the relation between the length of the original bar magnet and that arc. For that I used angle, it is equal to arc upon radius, right? And you got to the answer. So I hope you are clear with this concept. And if you are clear with this concept, let's move forward to the next problem. There you go. And it is from the chapter of semiconductors. And let me read the problem for you. It is problem 11 from the original paper. It says that in a half wave rectifier, the current flow. So you have been given a setup of rectifier. And this is the input AC voltage. This is the input AC voltage. Let me draw it for you. It is shown something like this, right? And you need to comment that current flow. So current or the output voltage is, output load resistance is kept over here, RL, right? And you need to figure out that current flows for which cycle. So this is your first cycle, this is your first cycle, this is your second cycle, and this is your third cycle. I hope you are clear. Yes, someone is giving the answer. Okay. Let me explain it for you how to get to the answer. So this is the problem based on the concept of forward and reverse biasing of a PN junction diode, right? So you have been given an input AC voltage for this part of the cycle. For first part of the cycle, you can see that this diode D, I'll write it over here. For the first part of the cycle, this diode D, it will be in for the first part of the cycle, this diode D, it will be in forward biasing, and you know that in forward biasing, the PN junction offers almost zero resistance, right? So you can replace it with the help of a conducting wire. So if this diode D is replaced with a conducting wire, you can see that the current will flow through the circuit, and you will get the output across the load resistance. For this case, you will get the output across load resistance, right? Now, for the second part of the cycle, you can see that this diode D, now this time the polarity will be reversed. This part which was initially, see, the diode will be in this condition. This is the diode, so this will be negative and this will be positive. So this becomes reverse biased, right? So for cycle 2, your diode will be reverse biased. That means that it will not allow the current right only for every half cycle of input signal. Yes, so for the first part, the diode was in forward biasing. It was allowing you the current to flow, and you were getting the output across the load resistance. But for the second part, the diode, it became the reverse biased, and in the case of reverse biased, you know that it will provide a large amount of resistance. In that case, you will not get any load across the output resistance, or you can say that the current is not going to flow. Again, for the third part, again, it will have the similar polarity as it was in the first part. So again, for the third part of the cycle, the diode will again be in the forward bias and it will behave as a conducting wire. Since it behaves as a conducting wire, the current will flow through the circuit. You will get the load across the output resistance, and that's how you will determine. So what are the options saying? The current flows. So you need to pick the cycle in which the current flows. So first says that during the first and third half cycle. Yes, the current flows only for the first and third half cycle. This one is correct for this part and for this part, right? Now, during second half cycle only. No, current does not flow during the second half cycle. Let's talk about the third, during first and second half cycle. No, not for the first and second, it's only for the first and third. So this one is also wrong. And during second and third half cycle, no. So option 1 is the correct answer to this problem. Yes, NEET aspirant has given the right answer as option 1. Option 1 is the correct answer. Now suppose that what should be the answer had the diode, one diode would have been placed like this. If I add one more diode like this, then this will become a full wave rectifier, right? So let me draw the output for you. So if this is the input voltage for the half wave rectifier, this is the input. For the half wave rectifier, you will get the output as something like this, right? And suppose that you have a full wave rectifier. So you will get the output like this. So I hope you are clear with what is the difference between the full wave rectifier and the half wave rectifier. All. Yes, all. You will get the output in every cycle. If this was the case, suppose that I had connected one diode over here, right? So for the first half cycle, what will happen that this diode will be in forward bias, this diode will be in reverse bias, and you will get the current across the load resistance. And in the second cycle, this will be in forward bias, this will be in reverse bias, this will be in forward bias. So for the second cycle also, you will get the load across the output, you will get the current, or you will get the load across the output resistance. So for the full wave rectifier, you will get the output load for each cycle, either for the first or the second or the third, because you have two diodes. If one is in forward bias, the other one will be in reverse bias, and if one is in the reverse bias, the other one will be in forward bias. So in either case, you are going to get the load across the output voltage, across the output resistance. So that's the basic difference between the output full wave rectifier and the half wave rectifier, right? And if understood the concept, let's move forward to the next problem. And there you go. Let me read the problem for you, and it is a problem 24 from the original paper. It says that identify the semiconductor device whose VI characteristic are given below. So you have been given the VI characteristic, and if you know the answer, you can put the answer in the comment box. Okay, so I have been given a VI characteristic like this. So this is V and this is I, right? This is I, and it is given something like this. This is VOC and this is ISC. Okay, so this is a standard question. You need to remember the IV characteristic for different devices, and this is the device. This is the IV characteristic for solar cell. What is VOC? Yes, what is VOC? Anyone can give me? Can you tell me what is the meaning of VOC? It is open circuit voltage. It is open circuit voltage. And what about ISC? What is ISC? So VOC is your open circuit voltage and ISC is your short circuit current. This is the IV characteristic for the solar cell. It is drawn in the fourth quadrant. So key points need to be taken into consideration. It is drawn in the fourth quadrant. It works in no bias condition, and your VOC is open circuit voltage and your ISC is short circuit current, right? So correct answer should be option 3. Now what about the IV characteristic of a Zener diode? So let me draw the IV characteristic for a Zener diode. It works in reverse bias, so it will be in the third quadrant only, and it will be something like this, right? So this is the IV characteristic for the Zener diode. What else? What else do we have in our option? So this is not for Zener diode, LED and photodiode. So can anyone give me the answer that in which quadrant the IV characteristic of photodiode will lie? Someone is asking question kidhar se attempt karu. You need to enroll in our test series AIATS Plus, and there you will get the question paper which we are discussing over here. So yes, third. Yes, very well. For photodiode, sir, where is the question paper? Dear student, you need to enroll into the program to get the question paper, and these are the questions from the original paper only. Yes. So let's get back to the topic. So photodiode, the IV characteristic for photodiode, it will again lie in the third quadrant only, right? Yes, option 3, solar cell is the correct answer. I am discussing about the IV characteristic of different other different options. For Zener diode, I showed it to you. It works in the reverse bias. Solar cell, it works in no bias condition. I have explained the meaning of VOC and ISC, and this graph is in fourth quadrant. For Zener diode and for the photodiode, the IV characteristic will lie in the third quadrant because they work in reverse bias. Yes, for photodiode and for the Zener diode, both will lie in the third quadrant because they work in the reverse bias condition. Yes, so this one is also wrong and this one is also wrong, right? Okay, if anyone is having any doubt, you can put your doubt. LED first. Yes, LED will first. LED will be first. Yes, if anyone is having any doubt, you can give me the answer. You can ask the doubt in the comment box. I'll wait for your doubt. Okay, no one is having any doubt. Everyone is studying very hard. Okay, dear students, if you are not having any doubt, with this I'll end my session, and these are the problems that I kept in my mind to discuss with you. I hope I made the concept clear regarding these problems. And with this I'll end my session. Thank you very much for watching this video, and please be tuned for more such videos which will be there in the upcoming future. And all the very best for your examinations. Thank you.